pleasure to introduce our speaker today, Anurag. He recently got his PhD from the University of Tennessee in Knoxville, but most of his PhD work was actually conducted on LTX, which is the subject of today's talk. So he spent a lot of time at PPPL and around Princeton, which is where I know him from. So yeah, without further ado, let's get started. Anurag, please take the floor and take it away.
Okay, good. Hey, everyone. I'm Anurag, and I'm a postdoc at the Lithium Tokamak experiment group. My talk today is going to be about plasma surface interactions in as it pertains to LTX and what a low recycling boundary is and what its implications are for fusion devices. Okay, just, these are my I'll not co-authors, but collaborators. And LTX itself right now is a pretty sizable collaboration, and it has collaborators and folks working on site from multiple institutions. These are just some of them. All right, so I don't need to remind this audience that the general idea of magnetic fusion is to create a device that exhibits enough magnetic pressure to confine the plasma within it. This ratio is called beta, and it's an important design parameter. Once you're able to do that, you need to confine this plasma for long enough for it to generate positive energy that can then be harnessed to do useful things. And unfortunately, first principles estimates of these confinement times are hard to come by. So we end up with these power scaling law expressions that look somewhat like this. Typically, most these energy confinement time power scaling laws have a functional dependence on a whole host of things, but usually by a strong dependence is on the size of the machine. So a general solution there is to just make these devices bigger. But this is where LTX comes in, and this is where it's kind of interesting because LTX seems to break these energy confinement scaling laws. So the way to read this plot is this expression plotted against itself. And then if you scatter plot LTX energy confinement times on top of that, you see it exceed the slope of 1, sometimes by a factor of 3. Just to give you an idea of the scale of the device, it's not a big machine. So this is the cross section, and that's the device in comparison to a bunch of average human males, and you can tell how many of them are Americans by counting how many of them are smiling. LTX was recently upgraded to LTX-beta. This is specifically the LTX-beta upgrade tool. The upgrade involved addition of a neutral beam, addition of active charge exchange and combination spectroscopy, addition of a sample exposure probe, which I'll talk about, a soft X-ray system. The interferometer was upgraded, addition of a reflectometer system, and new evaporators, along with a whole host of other things. This is not an exhaustive list. There's a whole bunch of diagnostics that I've not shown here because it would get too crowded. These are the things I've been involved with. I've designed and commissioned some. I've assisted in designing and commissioning of the evaporators, for example. For a while, I've been a primary user of the filter scopes, and I've recently recommissioned the Lyman alpha diode array and the machine's supersonic calculator. I'll talk about these towards the end. So just to give you an orientation, the machine operates in a limited configuration. So if you hear me say scrape off layer, it's a limited scrape off layer, not the conventional divergent scrape off layer, which is usually thin. And if you hear me say mid plane, I'm usually talking about colloidal mid plane. And if you hear me say high field side, limiter. That's this point on the copper shells. And if you hear me say low field side, I'm usually talking about the colloidal low field side. The specialty of the machine is inside the vacuum vessel. There are these copper shells that are conforming to the shape of the plasma. And on the inside of the copper shell, a stainless steel liner of about half a centimeter thick is explosively bonded. This is because we wanted to use lithium as a surface plasma facing component. And the way to do that was to evaporatively coat these liners uh, with, with lithium, but copper and lithium are bad combinations. So there was a need to line these up with stainless steel. Copper for conductivity, stainless steel for lithium. Okay, so I'll summarize my talk to begin with. I know that's unconventional, but I find it helpful in the sense that we could revisit the same slide towards the end, and maybe you can tell me for yourself if I've been able to convince you of these conclusions that I'm drawing from this body of work. The first is that LTX has demonstrated improvements in plasma confinement with employment of evaporative lithium coatings. There's pretty clear evidence of that, and I'll show you that evidence in a little while. And LTX results actually show first direct in-vacuum identification lithium compounds on a token's first wall and help identify how they affect plasma performance. In its current state, LTX-beta is ready to answer some important questions about feasibility of lithium as a PFC. And more importantly, perhaps for this audience, this is a hands-on device. It's mostly run by students, postdocs, and here's my overview. Oops, I got stuck. All right, there it is. Here's the overview of the talk. I'll start with lithium as a plasma-facing material and its properties. I'll then highlight some experimental physics results from LTX, followed by some physics and social science results from LTX-beta, followed by what we are doing now and kinds of questions that keep me up. Okay, so lithium is special because it has two properties. It can reduce recycling by retaining hydrogen, and because it's a low Z material, it can reduce radiative power loss. And so, before I go any further, just to remind people who might not be familiar with this terminology, when I say recycling throughout the talk, I'm talking about fuel recycling, not material recycling, which is fuel recycling in this context is just the ratio of flux of hydrogen neutrals from the wall to the spray buffer layer and flux of hydrogen ions from the spray buffer layer to the wall. The important thing about lithium is that it has been demonstrated by offline experimental investigations that liquid lithium especially can soak up and redeem hydrogen in a 1-to-1 ratio, typically forming lithium hydride. As the ratio of lithium to hydrogen approaches 1, the lithium hydride solidifies and it's no longer useful. This started in mid-90s when Tom Ronlin, who I think is one of the principal authors of UH, demonstrated on a bunch of UH simulations that the temperature profiles flatten out as you reduce recycling. And then that was followed by neoclassical transport investigations by several papers written by Leonard Thakral, and one I'd like to highlight by Cato and Hazeltine called isothermal Tokamak. So they basically looked at neoclassical transport and said, okay, what happens if your temperature gradient terms go to 0? And that would mean that your ion temperature gradient and electron temperature gradient driven transport is reduced to nothing, which explains why confinement would improve. Now, in addition to that, because liquid lithium, especially, is a low Z material, it has no material erosion issue because you can just replenish it if you homogeneous loop. There's no neutron damage because neutron damage is typically structural in solids, and there's no structural damage for liquids. There's dramatically reduced radiative power loss because most of these radiative power loss uh, processes depend strongly on atomic number, and they reduce dramatically if you take really low-Z material like lithium. So this is the plot of radiative power loss normalized by the product of uh, plasma density and impurity density at say about 10 keVs, which is where uh, functional fusion reactors might operate. You can see a 5 orders of magnitude drop. And you can run this sort of back of the envelope calculation for something like eta and get dramatic numbers. And it can be shown, and indeed this has been shown. This is a plot straight out of Dolan's textbook. That as you reduce atomic number, the maximum allowable impurity concentration for ignition actually increases by orders of magnitude. So it can tolerate, the core can tolerate much more lithium in it than it can tolerate tungsten, for example. Okay, so all of that is nice, but what has LTX been actually able to demonstrate? And that's what I'll talk about in the next few slides. Keep in mind, these are results from LTX, not LTX-beta. That'll come next. The first demonstration was using Thomson scattering. LTX in an ohmic regime was able to demonstrate that these temperature profiles indeed do flatten out. So this is a density line integrated density phase from an interferometer. And these pulses are the driver pulses for the high field side buffer. And it was observed that the Thomson scattering system was stepped through, and Thomson scattering profiles were taken multiple time points. And it was observed that after you terminate this gas buffing, these temperature profiles relax and flatten out all the way towards the edge. So that was evidence that there is indeed reduced recycling towards the end of the shot. At the same time, transfer estimates of energy confinement time in comparison to neo-Alcator scaling confinement time showed an improvement towards the end of the shot, where the energy confinement time can reduce as the density drop. And other estimates of edge core temperature showed that edge core temperature rose and gradually matched up to core electron temperature. There are other features to this behavior, primarily in the spray off where the collisionality drops to I think less than 0.1, and that puts it in the banana regime, where basically means neoclassical effects cannot be ignored in the spray off anymore. The edge density also reduces by an order of magnitude or 2 orders of magnitude after lithium applications. And if you try to estimate connection length by equilibria provided safety factors, you get a connection length of about 5 to 10 meters, and then if you try to estimate soul transit time, that turns out to be much less than the phase angle scattering time. So you can then make the argument that most of these ions and electrons are actually mirror confined in a spray off layer that doesn't have a lot of collisionality. So all of this indicates that you really do need kinetic modeling of the spray off layer. But for now, we've been talking about using sheet limited models for some back of the envelope estimates. All right, so the others, and this was surprising, the other result out of LTX for surface science, where Matt Lucia, who was a PhD student at the time, used this diagnostic called MAP, which was the materials analysis and particle probe. A MAP had a probe head that could be inserted into the machine through a gate valve, exposed to plasma and residual vacuum. It could then be retracted, and you could do X-ray full electron spectroscopy studies on it. XPS is a surface sensitive technique, and I'll get to that, but it can give you elemental compositions. And it was noticed that no matter what you do, once you start evaporating, the surface accumulates more and more oxygen to the point that this oxygen and lithium ratio settles to about 2, which indicated the presence of something like lithium oxide. What was even more surprising that during all of this, plasma performance did not seem to decay. And I'll get into that in a little bit. So just a little primer for those who aren't familiar with XPS. XPS is a surface sensitive technique where you shine photons of a known wavelength at a surface, which can then knock out core electrons. And if you detect the core electrons with the energy, kinetic energy they escape, you can identify the binding energy with which they were retained in the surface. This is a surface-sensitive technique because these electrons that are escaping from the surface typically don't have large mean free paths. So if you know the photoionization cross-sections and if you know the peak sizes of these various elements that are detected in a scan, you can typically figure out what the elemental compositions are. And in addition to that, if you have sufficient resolution, you can detect slight shifts in binding energy and identify if there are more than one compounds or if there are specific compounds on the surface. So this is an example of a really high resolution lithium scan done on Princeton University campus. And it clearly identifies that there are at least 2 oxygen 1s peaks and binding energies from literature can be used to attribute these to, say, for example, I've made the attribution lithium oxide and lithium carbonate in this case. Okay, but the issue with the LTX results was the LTX XPS system map just did not have enough resolution to identify what these compounds were, and that's where LTX-beta and its upgrades come in. For LTX-beta, we ended up designing a sample exposure probe that instead of mounting a high-resolution spectrometer on the machine, which is hard to do, A, because of space constraints, and B, because you need to operate the spectrometer in large swings of magnetic field. We ended up designing a simpler sample exposure probe that could expose these samples of stainless steel in the vacuum vessel. You could deposit lithium on it and expose it to the plasma, and then take it to a machine and do really high resolution scans. So this is a picture, for example, right after lithium evaporation, and I really like showing this. This is for the reason that this is the sample head pictured here as in comparison to the CAD drawing. And you see the evaporator in reference to the sample head here. And when you look at the picture, though, you see 2 shadows. This one is subtended by an E-beam filament that's somewhere over here that's used for breakdowns. But the second shadow is actually a lithium shadow. So that's a nice picture to have. Once we have enough lithium plasma and residual vacuum exposure, we wheel it down to the surface science lab, which is next door to us because PPPL has this really nice facility, and hook it up to a high resolution XPS spectrometer called the PHI, which wasn't working initially, and it's part of my job to fix it. And it turns out it works out really well because for the shortest duration, for the minimum duration it took for a map scan, it is equivalent to the transfer time to the PHI because the PHI operates at a much lower base pressure. And you can do these back of the envelope calculations to figure out if you're sitting in residual vacuum at, say, 10 to the negative 7 torr, for 10 minutes, what is the equivalent time at 10 to the negative 9 torr, for example? Once you do all of this, you can make a direct comparison with MAP. For example, this is a carbon C1S peak on stainless steel, and you can see the resolution improves by like a factor of 2.5. Okay, all of this is nice, but what do we learn from here? Well, a bunch of things that I'll highlight in the next few slides. Uh, this is from the first use of the sample exposure probe, where we started with bare stainless steel and exposed the machine and the sample exposure probe to a neon flow discharge conditioning cycle. And when we took a scan, we saw that the carbon reduced and the oxygen increased and the iron increased. This is likely from the neon glow discharge sputtering away the surface carbon. This is, if you're not a surface scientist, this is not a known fact to everyone, but every surface that is exposed to air typically has a few nanometers to a few tens of nanometers of carbon on top. Anything that you touch, anything that is exposed to air. And that's what was happening. The sample exposure probe in the machine was then exposed to a bunch of lithium discharges on bare stainless steel, followed by lithium evaporations. Now, as you see, beyond lithium evaporations, the iron and chromium peaks completely disappear. All you see on the surface is lithium oxide and carbon. And depending on how close to the lithium evaporations you take a scan, you get different surface concentrations of lithium, oxygen, and carbon. So if you take it immediately after lithium evaporation, you see much higher lithium, slightly suppressed oxygen, whereas if you take it quite a while after lithium evaporation, you see that the lithium concentration reduces and the oxygen concentration increases. And that's consistent with the previous data I've shown you. But that's not good enough. Because we had high resolution, we could go ahead and identify what these surface species were. So a lot going on here, and I'll walk you through this step at a time. The first thing to notice is these are arranged in time from lithium evaporation. So the first row is 1.5 hours after lithium evaporation. A second row is about a day after, and the third row is about a week. The first thing you see is the surface is rich. It's not as simple as you put evaporative lithium coatings and you have a lithium PFC. That's not the case. You have multiple species: lithium oxide, hydroxide, hydrocarbons. There's some lithium carbide floating around. And I'd like to point out that in the best case scenario, you do end up with an oxide coating on the lithium. And my estimates is in given LTX-based vacuum, that's about 1.2 nanometers. Keep in mind, LTX has exemplary vacuum conditions of most tokamaks. It operates at a base vacuum of mid to low 10 to the -8, whereas bigger tokamaks operate in -6 and -7. So if you do this in a bigger tokamak, this would be bigger. It would be thicker, the oxide coating. In addition to that, you notice that the primary surface constituent is actually lithium oxide. That's the largest piece in the system. And you notice that as time goes on, this hydroxide peak increases. So this is actually fairly consistent with this data set, where as time went on, the surface gathered more and more oxygen, and as time went on further, the ratio of lithium to oxygen reduced and started dropping towards something less than 1, which would indicate hydroxide presence. So in summary, this was the first in-vacuo observation of lithium compounds on a compounds evolution on a tokamak surface. But all of that is fine. It would be more interesting to know how these affect surface conditions. These surface conditions impact plasma performance, and this is particularly interesting because if you recall, I mentioned that although the surface oxidizes, the plasma performance does not decay. So to study that, we did this little experiment. We exposed the sample exposure probe to the LTX at the toroidal midplane, and at the same toroidal radius, we inserted a single laminar probe. In addition to that, we focused a few fiber bundles on the sample exposure probe head that could look at lithium, oxygen, and deuterium lines, hydrogen lines. So it was lithium 2, oxygen 2, and H-beta. And we made a comparison of what happens if you have really old passivated lithium coatings, and then you deposit some lithium and wait a week and make comparison. So this is a direct comparison. We saw that the plasma current and duration definitely increased. The oxygen emission in particular goes down, and lithium emission goes up. We also saw that towards the end of the shot, as you eliminate gas puffs, the density goes down and the temperatures go up, which is consistent with the edge heating up. This density decay in oxygen emission and rise in lithium emission was pretty consistent. There was a sharp decrease after lithium coatings, even if the lithium coatings were a week old, and it kind of stayed that way for a while. In addition to that, it looks like these weak old lithium surfaces, which is lithium oxide primarily on the top, were doing much better pumping to sustain the same line integrated electron density, say this phrase. We had to pump in 2.5 times more gas. And the difference between gas puff with plasma and with plasma and with no plasma was substantial as compared to passivated lithium, where there was little to no difference. Okay, that's good, but what did the surface say? Well, if you take an XPS scan here before, you see a much larger hydroxide peak if compared to if you took the XPS scan here. So the conclusion seems to be that as long as the PFC is just lithium oxide, it's actually okay. That it's okay for this lithium to oxidize, and there really is no way to escape that. But as long as that oxidation stays to lithium oxide, it's probably fine. All right. So what's next? What are the current capabilities, and what questions are we trying to answer now? There are a few different things, so this might feel a little disjointed, but please bear with me. I assure you there's a connection. The older lithium evaporators look like this. There was a coil of tungsten inside which sat a mesh of stainless steel, a tiny little basket, into which we would insert coupons cut out of lithium foil. And this was inserted facing this way into the machine. And because of the way it's structured, you need some structural elements to hold the coil and the basket and the thermocouples in place. There was some shadowing from these elements, but some modeling indicated that because these large blocks in the front that are provided for structural support and to hold the filament, there might have been some shadowing on the center stack. And that although we were reaching pretty good coverage, we may not be entirely coating the limiting surfaces because that's where the plasma limits on the high field side center stack shell. So to sort of fight that, we modified the design. The basket is now taller, can take much more lithium, and these structural blocks in the front have been completely eliminated. There's also a tangent reflector in the back that can improve our coverage. In addition to that, there's a new upgraded Lyman alpha photodiode array. This is basically an array of 20 photodiodes that sits behind a Lyman alpha filter shown in this orange housing, and it can view the shell through this gate valve. This is important because Lyman alpha emissions have particularly low specular reflection, which is useful for an all metal machine, where if you look at hydrogen alpha or hydrogen beta signal as a proxy for recycling, you're probably deluding yourself because of large reflections from other places in the machine. And this has been recently commissioned, so this is what that data looks like. If this is a shot, 102387 was fired, I think, a week ago. And as the plasma compresses and collapses on the high field side, you see the video is not working. Well, you see these. See if I can. There it is. So as the shot progresses, you see the plasma limiting on this D8 D9 diode, You see the signal increase, and finally the plasma collapses. And if you freeze it, you can view it at one particular time. You can get the Lyman alpha emission intensities. And you can then relate that to recycling by using direct interpretive modeling. Okay. Another addition is an off midplane Langmuir probe. The old Langmuir probe doesn't exist anymore, and I can talk more about why. But this midplane probe has been installed, and it so far survives 40 millimeters past the shell from Predator. The only way to fit this on the machine was to hang it upside down over the interferometer. So this is before the installation. If you can make any sense of this picture because it's so crowded, that's the machine. The blue taped portion that you see are the vertical blue coils. And this is the interferometer cage right here. So because the interferometer needed a direct line of sight into the vessel, we could not mount it on the floor. We had to hang it upside down. And if you ask me, I'll seriously tell you with a straight face that I designed for this 3 mm clearance from the interferometer cage, and I did not get lucky. The other addition to the machine is a supersonic gas injector, which has been mounted on the top, and we are in the process of commissioning it. We have to get the gas puff programming right for this to work. But the general idea is, if you use a supersonic gas injector, you can probably get past the scrape off there and fuel the core directly. This is ongoing, and hopefully this will work soon. So, what do I need to do with this? There are a bunch of unanswered questions here. One is I've given you this entire story of performance improvement and recycling reduction without giving you a recycling estimate, and that really is a big open question. Is what is that number? So our hope is with the new Lyman alpha array and an estimate of edge density and temperature using the Langmuir probe, and some interpretive modeling using neutral particles modeling code like Dega2, we can come up with an estimate. And once we have an estimate, we can try to answer a bunch of really important questions like how does recycling change as a function of area confinement time, for example? And how does it change as surface conditions change? Or how does it change, or is it more or less important compared to impurity sequestration? You notice that the oxygen signal in the filter scopes goes down for passivated or partially passivated coatings. Is it more important that the lithium is gathering the oxygen, or is it more important that lithium is reducing recycling? And more importantly, the flat temperature profiles that we've observed in the past were for ohmic plasmas. They were fueled by gas puffs, which is not scalable. You cannot have a machine like ITER fueled by gas puffs. It has to be neutral peak fuel. So does LTX exhibit lower recycling with beam fuel plasmas? These are all very important questions that I think we're pretty close to answering because all the tools are in place and the machine is running. Okay, so I'll summarize again. LTX has demonstrated improvements in plasma confinement with employment of evaporative lithium coatings for ohmically confined plasmas. LTX results show the first direct in-vacuum magnification of lithium compounds on a Tokamak surface first wall, and it has helped identify how they affect plasma performance. And we're about ready to answer some important questions about the feasibility of lithium as a PFC. And again, more importantly, this was all done by students, postdocs, and collaborators. Yeah, I'm done.
Okay, that's great talk. I have a couple questions myself, but if the audience has any, please feel free to let us know or to paste them in the chat. Yeah, sweet. So we got one already.
So in the beginning of your talk, you mentioned some papers by Leonid Zakharov. So
yeah.
he spent a rather long time at Princeton. Are his ideas still followed? And the second point he proposes for let's say, fusion reactor, continuously flowing lithium, which is then pumped out and refreshed and so on. So, and in this respect, what you find is, let's say, ceramic particles. This could be a problem that you could, for instance, obstruct your pump.
Could you repeat the second part about the ceramic particles?
Yeah, so you find lithium oxide, hydroxide, and so on. And in other machines like T10, after lithium vaporization, at the end of the machine time, they found ceramic nanoparticles on the wall. So the wall was completely white, and it consisted of lithium oxide particles.
Yeah.
And if you think now of Zakharov's idea of continuously flowing lithium and being pumped out to refresh and so on, these particles could be a problem for the pumping.
Yeah, so you'll have to humor me. So the first part of the question, Leonard Zakharov was indeed at PPPL for a while. Are his ideas still followed? Leonard Zakharov is a theorist, and I have nothing but respect for theorists, but they can be sometimes optimistic in their projections. And I think, yeah, LTX exists, so Leonard Zakharov's ideas are taken seriously, but with practical constraints. Yeah, the second point of your question, I don't know what TJ2's background pressure is, but I think oxidation rate really does depend on your background pressure. So I think it's liquid lithium flowing walls are feasible as long as you do it cleanly. And of course, you'll get some oxidation on top, but if you have good pumping and if you have no to few leaks into the machine, at really low vapor pressures, the oxidation can be limited enough that I think that the liquid lithium wall can sustain.
Okay, thank you.
Very nice talk, Anurag. Thanks.
Hey, George.
Hi. I had a question about the significance of the flat temperature profile, and I think this is reflected a little in the chat. So is one way to interpret that you can reach, higher edge temperatures, and therefore the machine in principle could support higher core temperatures if there were more heating. Is that, like, in a sense, if heating were a infinite resource, that there would be, that you're underutilizing the device, that there could be more heating and you could reach higher temperatures? Or is this...
Oh, okay. Yeah, I see what you mean. Yeah, I don't know. I don't have a straightforward answer to that.
Okay.
Yeah, I mean, yeah, I think we can start thinking about it once we start like getting recycling numbers for beam fuel plasmas, right? Because if you have like good recycling and these edge temperatures are hot, and in addition to that, if you try to beam fuel it, then that's a different beam fueling regime than something like D3D, for example, where the core temperatures are peaked. Right? So it's not at all clear to me what would happen actually.
Okay.
Yeah, I'm sorry, that's not satisfying.
No. This guy was just scared. Thanks.
And, and like George mentioned, there's a question in the chat along these lines, like would the temperature be flat at 15 keV all the way out to the edge in a pilot plant?
That's
so I guess. Yeah. I guess the question there, I mean, George's question maybe is more like what happens to core peaking, but you could also flip I'm curious, if you flip where you're looking and you look only at like the edge, the scrape-off layer, flat temperatures, like would you expect that to raise up to like very, very hot temperatures that might like be dangerous for the wall, or is anything like that,
No,
or is there still something limiting it low?
yeah. So again, these are separate questions.
Hmm.
It's not clear whether it would be dangerous for the walls, because I think, and there's a Dick has written a white paper about it, and he's more of an expert in this, but he seems to claim that as edge temperatures increase, your scrape off layer width broadens, and that has to do with this argument of trapped and passing particles. Um, so that's one side, which is, again, it needs to be fleshed out. And if what was the first part again?
I mean, I guess just um, like what would, are you expecting a completely flat temperature in the scrape off layer on like a hotter device?
Yeah,
And if
that's
so, like how hot? I guess
that's what the theory predicts, that if you,
yeah.
if you reduce recycling, these profiles do relax. Uh, and yeah, I would say, yeah, that's expected. It's certainly demonstrated at hundreds of EVs of temperature in LTX. I don't know if there are other mechanisms that exist that would resist this profile relaxation at higher temperatures, if that's your question. Uh, that's unanswered because that just needs to be experimentally verified.
Great. Yeah. Thanks.